You know that feeling when you've got a calculus exam looming, you're staring at a page full of rational functions, and the limits are literally just starting to blur together? Yeah, I see you. I know exactly how stressful that can be. So take a deep breath. Welcome to this explainer. Think of this as your ultimate high-yield study session. Today, we're going to conquer those complex functions, decode those tricky boundary lines, and get you absolutely prepped to crush this topic on your test.
Okay, let's dive right into this. We gotta start with the word itself. Asymptote actually comes from the Greek word asymptotes, which literally translates to not falling together. And honestly, that is the perfect way to visualize it. An asymptote is simply an invisible boundary line that a curve chases. It gets closer and closer and closer, but it never quite catches it or falls together with it. It's basically the ultimate mathematical game of tag. So here's our game plan for today's session. First, the invisible boundary lines. Second, vertical asymptotes, aka the walls. Third, horizontal asymptotes, the horizons. Fourth, oblique asymptotes, or the slants. And finally, number 5, the rational function shortcut. All right, section 1, the invisible boundary lines, and visualizing the limits of functions.
Now, to really master asymptotes on a test, we have to zoom out. We have to look at the behavior of curves in the large, using the strict rules of limits. And what's really interesting about this is a common misconception that trips people up. In everyday life, right, if you draw a line and a curve getting closer and closer on a piece of paper, the ink eventually just bleeds together. But remember, mathematical curves and lines are idealized concepts. They have absolutely zero width. That means no matter how far out you go, as your coordinates tend to infinity, the distance between them shrinks to zero, but they always remain distinct. You really have to use pure logic rather than just your physical experience to wrap your head around this.
Moving on to section 2, vertical asymptotes, the walls, and evaluating limits as x approaches a constant. You can think of vertical asymptotes as the impenetrable brick walls of our coordinate plane. These are the places where your function's value suddenly spikes and grows completely without bound. The formal exam definition basically states that the vertical line x equals a is an asymptote if the limit of your function as x approaches a from either the left side or the right side shoots straight up to positive infinity or plunges straight down to negative infinity. But here's the real trick for your exam. Finding these walls usually boils down to just looking for the exact spot where the denominator of a rational function becomes 0 while the numerator is non-zero.
Let's walk through a specific test-style example so you can see what I mean. Look at the function f of x equals x divided by the quantity x minus 1. Ask yourself right now, what makes that denominator 0? Exactly, x equals 1. Now imagine as x approaches 1 from the right side, say 1.001, the numerator is basically 1. But the denominator? It's a tiny, tiny positive number. Divide 1 by a microscopic positive number, and the whole thing just explodes to positive infinity. But if you approach from the left side, let's say 0.999, that denominator becomes a tiny negative number, which sends the whole thing plunging down to negative infinity. So the curve spikes wildly right at that invisible wall of x equals 1. Let's move to the next idea and see how this builds, because you should notice a pretty stark difference in our approach here. For vertical asymptotes, we evaluated the limit as x approached a finite constant, like the number 1. But as we prepare for our next concept, we completely flip the script. Now, we want to know what happens when x itself becomes infinitely large or infinitely small. Which brings us to section 3, horizontal asymptotes, the horizons, and looking out to infinity. So we're shifting our focus here from those vertical brick walls to distant, flat horizons. The rule is that the line y equals c is a horizontal asymptote if the limit of the function equals that constant c as x goes to negative or positive infinity. Just remind yourself when you're sitting there in the exam room, evaluating this is really just a matter of plugging in massively huge numbers, like 1,000,000 or 1,000,000,000, and watching the behavior of the graph stabilize to a totally flat, constant value. And this brilliantly illustrates a major curveball your professor might just throw at you. Take the arctangent function. As x approaches positive infinity, the curve levels off at a horizon of y equals positive pi over 2. But if x approaches negative infinity, it flattens out at y equals negative pi over 2. So yeah, a single function can absolutely have two completely different horizontal horizons depending entirely on which direction you're traveling. Pretty wild, right? All right, section 4, oblique asymptotes, the slants and tackling diagonal boundaries. Now we arrive at what's arguably the hardest asymptote question you're going to face on your exam. What happens when the boundary is a slant? The mathematical definition looks incredibly dense, I know, but let's break it down together. An oblique asymptote is literally just a diagonal line with the familiar equation y equals mx plus n. It exists if the limit, as x approaches infinity, of your function minus that diagonal line exactly equals 0. What does that mean in plain English? It just means the empty space, the actual vertical difference between your complex curve and the simple diagonal line, shrinks to absolutely nothing at infinity. They essentially just merge into the exact same path. So the crucial point is knowing how to actually find m and n when you're staring at a blank test paper, sweating the clock. You absolutely need to memorize this exact two-step formula. Step 1. Find your slope m by taking the limit of your function divided by x, as x approaches infinity. Step 2. Find your y-intercept n by taking the limit of your function minus mx. Let's just quickly power through a calculation so you can see how beautifully this proves out. Take the function f of x equals 2x squared plus 3x plus 1, all divided by x. Step 1, divide that whole thing by x, which gives us 2x squared plus 3x plus 1 over x squared. As x goes to infinity, the limit is simply 2. So boom, our slope m is 2. Step 2, take the original function and subtract our new mx, which is 2x. A little bit of algebraic cleanup leaves us with a limit of 3. So n is 3. Put them together, and just like that, our slant asymptote is the line y equals 2x plus 3. Okay, final section. Section 5, the rational function shortcut, also known as the ultimate exam cheat code. You're going to want to pay very, very close attention here because I am about to save you a massive amount of time on your test. Behold the cheat code matrix. By simply comparing the highest power or degree of the numerator and the denominator, you instantly know your asymptote. Okay, check this out. If the numerator's degree is smaller than the denominator's, your horizontal asymptote is always exactly y equals 0. If the degrees are identical, just divide the leading coefficients. For example, 2x squared over 3x squared instantly gives you a horizontal of y equals 2/3. Now, if the numerator is exactly 1 degree higher than the denominator, you perform Euclidean division, and the quotient is your oblique asymptote. And finally, if the numerator is more than 1 degree higher, you have no linear asymptote at all. Let's lock this survival guide into your memory with some rapid-fire bullet points. Denominator goes to 0 while the numerator doesn't? Boom, you hit a vertical wall. Numerator's highest power is smaller, your horizon is flat on the axis at y equals 0. Both polynomials have the exact same highest degree. Divide those front numbers. Numerator is exactly 1 degree higher. Get ready to calculate an oblique slant. Seriously, this is your absolutely foolproof toolkit to double-check your limit calculus on the exam. But before we wrap up this explainer, I want to leave you with kind of a mind-bending thought. We've talked entirely about linear asymptotes today, straight boundary lines. But what if your function's numerator is exactly 2 degrees higher than the denominator? You wouldn't get a slanted line. You'd actually get a curvilinear asymptote. Your function would literally chase a parabola out to infinity. There's always a deeper, crazier level of higher math waiting for you, but for now, take these tools, master those limits, and go ace that calculus exam.